During my senior year of college, I found out that my best friend's dad had been diagnosed with terminal cancer. This changed the whole perspective that I had for what I wanted to do with my life, and made me realize that I wanted to make a difference with the engineering lessons that I had learned in my undergrad. It started me on a path that brought me to become a graduate student researcher in the field of biomedical engineering. During my first year at Wake Forest University, I had the opportunity to join a team that was working on a project that had been brought to us by Dr. Clifford Howard. He had realized that there were several issues with the current methodology used for the treatment of bile duct strictures. Strictures are caused by either a malignant or benign tumor that grows adjacent to the common bile duct, leading to an inability of the body to drain bile from the gallbladder into the duodenum. This backup of bile in the body system leads to increased levels of bilirubin, which can lead to patient discomfort as well as a condition known as jaundice. The current methodology, the current standards for treatment of these conditions are to use either a plastic or a metallic stent to re-expand or open up the bile duct to restore drainage. However, both the plastic and the metallic stents have issues with stent migration and also with mechanical failure. This leads to the need to have additional rendition surgeries and increasing potential injury to patient as well as patient cost. So for our project, the goal of our project was to create a stent that both had anti-migratory features as well as the ability to resist mechanical failure due to the forces in the environment that it was placed. We started off with a design that had several features that were hooks that deployed out of plane as you expanded the stent radially. These hooks served as an anchor with the surrounding tissue wall, securing the stent in place. We took these designs and created 3D computer models using a software called SolidWorks. These 3D models were then imported into a simulation package called Abacus. Through the simulation package, we were able to recreate the mechanical loading environment that the stent would experience, being able to look at specific focal bending points of the hinge and the bodies, specifically looking at stresses and strains to create an optimized stent design. This stent design has since then been turned into a metallic prototype that was laser cut from stainless steel tubing and is in the process of undergoing testing both to validate our simulation model and to create benchmark values that will enable us to compare to other stent values, to other current available stents. My senior year, I had no idea that I would have the opportunity to work on a project that took an idea from conception all the way into the prototype, with the potential to be used to treat patients with the same type of pancreatic cancer that my best friend's dad passed away from. I look forward to future opportunities such as this to work on medical devices that can aid in the treatment of patients around the world. Thank you.